In the last video, we talked about dimensional analysis. So when we did, we came up with all of these dimensionless ratios, what we call dimensionless numbers or pi parameters, pi terms, that arose from those governing equations. And it turns out that people have been investigating this type of thing for a long time, and they've been using these dimensionless numbers to solve various types of problems. And typically we name these numbers after the person who discovered them. So we're going to spend this video just looking at some of the important dimensionless numbers that come out of this dimensional analysis and what they mean, what their significance is, and what they mean physically for a fluid. So we start with the Struhal number. The Struhal number comes from that time-dependent term, the time derivative, and it's basically the ratio between the inertia of the fluid and the convection of the fluid. So it scales the local inertia to the amount of fluid that's moving by convection. And it basically gives us a time scale for the behavior of the flow. The Euler number gives us the ratio of what we call pressure forces to inertia. So it's the pressure force acting on the fluid divided by the inertia of the fluid, or its resistance to motion. It's basically force over mass to scale the acceleration due to pressure forces. It's important when there are very large changes in pressure. And in fact, it's often written as a pressure coefficient or cavitation number. So the pressure coefficient just describes the change in pressure between some location and some reference location. The cavitation number measures how close a fluid is to what we call cavitating. So what happens is if the pressure in the fluid gets too low, it can actually boil without any heat input, and that's called flashing. And we want to avoid that because it can cause damage to fluid systems. We'll talk about that much later in the course. But we use the cavitation number to describe how close something is to that phenomenon. And the closer the cavitation number is to 0, the closer you are to cavitation. We also have the Reynolds number. The Reynolds number is probably one of the most important dimensionless parameters in fluid mechanics. It shows up in many important problems. And it's basically the ratio of the inertia of the flow to the viscous forces in the flow. So again, it's like mass over force, but in this case for viscous forces rather than pressure forces. And again, it's important for almost all types of flow that we're going to see in this class. We also can describe the Froude number. Now the Froude number is the ratio of fluid inertia to gravity forces. Typically it's important for flows that involve a free surface, like an open channel or a ship moving on water or something of that nature. We also have the Prandtl number. This comes from the thermal energy equation. And it basically relates the diffusion of momentum to the diffusion of heat. It's basically heat diffusion over momentum diffusion. And there'll be more about this in heat transfer. We'll talk about that more later, but it's very important for heat transfer. We also have the Eckert number. The Eckert number, again, comes from the energy equation, and it describes how kinetic energy is related to thermal energy. So it's the ratio of kinetic energy to thermal energy. It's usually very small. In fact, if you consider water, if water changes by 1 degree Celsius, that's the same energy change as a velocity going from 0 to 65 meters per second. So the kinetic energy is usually quite a bit smaller than the thermal energy. We also have the Weber number. The Weber number comes from boundary conditions, and it's basically the ratio of inertia of the flow to surface tension forces. So the Weber number, the Froude number, the Euler number, and the Reynolds number are all talking about relating forces to inertia, force to mass, basically. The Weber number is important whenever there's an interface between two substances, two fluids, and it actually comes up in many problems from the boundary conditions. And last, we have the Mach number. Now, we assumed when we derived our dimensionless numbers that the flow is incompressible, and because of that, we didn't come up with the Mach number in our equations. However, the Mach number is just the velocity of the flow divided by the speed of sound in the fluid, and it measures the compressibility of the flow. The higher the Mach number, the more compressible a flow is. So assuming incompressible flow, typically requires that the Mach number be smaller than 0.3. If the Mach number is higher than 0.3, then you have to account for compressibility effects, and you might have to deal with shock waves and things like that. So the question is, why are these dimensionless groups important? Why do we care? Well, if we rewrite the momentum and energy equations in terms of all these dimensionless numbers, we can ask ourselves a few questions. What if the Eckert number is small? If the Eckert number is approximately 0, it means that we can ignore the conversion of mechanical energy into thermal energy, friction, in the energy equation. So we can ignore friction heating in the fluid if the Eckert number is small. If the Reynolds number is large, then this 1 over Reynolds number on each side of the equation becomes very small. And we can approximate the flow as what we call inviscid. If the Reynolds number is very large, then we can neglect the viscosity and the effect of viscosity on the flow. So these dimensionless groups tell us which parts of the equations are important and help tell us where to focus our modeling and experiments in order to predict systems and describe systems. Now the other question is, what if all the dimensionless numbers for two systems are exactly the same? What happens if two systems have the same Euler number, Froude number, and Reynolds number, and Struhal number? Well, it turns out that the dimensionless velocity is going to be the same for those two systems. And that gets us into the idea of similarity, which is the topic of our next talk.